Hello, everyone. First of all, I wanted to thank you all for accepting this invitation and being here. My name is Mustafa Baboi from University of Geneva, Group for Energy Efficiency. And today with Frederick Bless from OST, University of Applied Science, Eastern Switzerland, we are going to present ASTRA, which is basically about automating the design and integration of industrial heat pumps. This project is funded by SWEET Decarb CH, which is a federal Swiss project for energy research for the energy transition. For the general attendees of this webinar, I would like to start with some statistics to know what we are talking about. So, as you may know, the latest statistics from IEA tells us that the share of industrial CO2 emissions globally is 9 gigaton per year, which is about 285 tons per second. And just to give you a sensible estimation of how big is this number, it's about 7 fully loaded 40-ton trucks every second. In terms of energy use, the final energy use of industry is around 180 exajoule per year. This is also equal to 8 warm shower for every individual on the planet, which is a huge number. And the assumption is that each shower takes 60 liters, and the amount that we heat the water is 30 degrees. So out of this 180 exajoule, around 2/3 of this energy is being used in form of heat in industry, and 40% to 50% in some countries it's more and less, but by average 40% of this heat is a suitable range in order to provide this with heat pumps for industries. So we are talking about big numbers. So the way we start the whole thing is basically with a table like this, which we call the process stream data. So here we have different streams in the company, in the site, and each stream has its own specifications like mass flow rate, CP value, the inlet and outlet temperatures, and the heat load that is dedicated to each stream. And with this, we are able to carry out a pinch analysis to be able to generate these pinch profiles, the one on top called composite curve, and the one on below is a grand composite curve. And what they can provide for us, I consider them as thermal signatures of each industry. For example, they can tell us how much heating demand we have at different temperature levels, and also cooling demand. So it gives us a good estimation of how much heating and cooling is needed at what temperatures. Another advantage of pinch analysis that really help us is in integration of heat pumps. Because if we integrate the heat pump in a wrong place, we will add to the utility demands of the site. For example, if we integrate the heat pump completely below the pinch, this is the pinch temperature. Here, basically, heat is a burden, and we want to get rid of it by providing cooling. And by implementing the heat pump, we are adding heat to a zone that heat is excessive. So it's not really a favorable action and is adding to our cooling demand. Also, if we implement it above the pinch point, we are basically extracting the heat from where heat is valuable and we need it, and we add the compressor power, basically power consumption, to the heat that we extracted and we provided. So here we are losing the magic of the heat pump, which is the COP of 3, 4, 5, let's say efficiencies of 300, 400, and we are replacing it basically with the electrical resistance with 100%. There's no difference between the two. So pinch analysis tell us that the best way to integrate heat pump is between the pinch point, where we can extract the heat from below the pinch, this blue zone that we see here. We have the waste heats, so we can extract from below the pinch and we provide it for above the pinch. And with this, we are not only reducing the cooling demand, but also we are able to provide the heating for where heat is needed. So in terms of, now we know where to place the heat pump. In terms of the integration, there are always different possibilities. For example, if you consider that we also have a gas boiler option, which in reality is also like this, and we consider that the share can be exchanged between the two technologies. Here we have the boiler, which is covering the majority of the heating demand, and we have only one heat pump unit with one evaporator and one condenser. And this shares and the placement of these units can change, their temperature level and size and so on. So here, for example, we see that the share of the heat pump is increasing compared to the boiler. So this is always changing between these two technologies. I mean, there can be several technologies, but as a base case, we consider the comparison between the gas boiler and a heat pump. And this is due to the energy price, the electricity price, gas price, and the technology cost that defines which technology is superior to use in each case. So in the previous case, we had one heat pump with one unit of evaporator and condenser. This can be two, as you see in this picture, and it can be at different levels. It can be three. So soon we realized that there are so many possibilities of having heat pumps in terms of number, sizes, their location, and also the way the interaction between these evaporators and condensers. And it turns to a huge problem that it needs a huge computational time. So that's the idea behind ASTRA. And now we are going to go through different aspects of ASTRA, what is able to do so far, and then we're going to talk about the future plans that we have for this model. So as I mentioned, we start with the pinch analysis, and we are able to generate these profiles. So we know where we are standing, what is the current situation of the company. And then we talked about this huge search space, so many possibilities that we have for integration. So here we are using a technique which is called Carnot-based pre-filtering technique. And with this, we are able to reduce the search space, and this will save us a lot of runtime. And then we pass it through the superstructure optimization. So here we are having less possible, let's say, integration plans. And with this, we are able to reduce the runtime from hours to seconds and under a minute. And what we consider in the superstructure is different possibilities of heat pump. For example, we have the conventional cycle, the four main components: superheater, desuperheater, pre-saturators, economizers, multi-stage expansion, and compression. And what is happening here is that the algorithm is optimizing not only for different configurations to see which one suits the best for our industrial case, but also for different working fluids, because these two, the configuration and working fluid, also have effect on each other. And then within this optimization platform, basically we are simulating the heat pump, and we always need to have a realistic estimation of the efficiency of the compressor. And for this, we try to train an artificial neural network with thousands of test data from famous compressor manufacturing companies like Bitzer, Gea, Maikawa, and we are able to estimate the efficiency by basic thermodynamic inputs like temperature and pressure of evaporation and condensation, and also the type of the working fluid and characteristics like inlet density of the flow that is entering the compressor. And we are able to estimate the isentropic efficiency with the R square of 0.98. And then finally, we will have the techno-economic results for the heat pump integration. We will have the COP, the capital costs, operating costs, and the paybacks, and so on. So these outputs would be useful for heat pump manufacturers, also for equipment manufacturers like heat exchangers, compressors, and so on, because it will give them a clue that in case that we do some sectoral analysis, for example, for dairy, food, or other sectors, it will tell us what is the most frequent configuration that comes out for these particular industries. So then the manufacturer knows what is the most valuable target in the market. Then they can focus on production in scale for that particular sizes or temperature levels and so on. They can shape their, let's say, marketing kind of. It's also useful for consultants that they can provide solutions for industries, but also can be used by the end users, the industries themselves. So they can use the model in order to have a rough estimation that uh, what size of heat pump or at which temperature levels they can integrate and how much it will cost. And in the end, it's also useful for policymakers because in case we do some sensitivity analysis, we will see that what are the thresholds for energy prices that is kind of motivating the end users to implement heat pumps instead of their current technology if it is a gas boiler or something else. Here we have a result of this optimization algorithm that I explained. It's a adaptive genetic algorithm. And on the right side, we see that it's beautifully starting to narrow down the search space and settling in the zones, in the levels that even with an expert intuition, we would expect if we have, let's say, 2 units, they will stay in these zones. And on the left side, we also see the evolution of the solutions. And what is interesting is that we see there are so many solutions that they're not much different from this star point, which is the best, let's say numerically is the lowest total annual cost. But there are so many similar solutions. And this shows that we can provide a range of solutions for the user, and user can choose based on their criteria that what is exactly matching their needs. So far we talked about subcritical heat pumps because we were talking about constant temperature of evaporation and condensation and this superstructure that I explained to you. But now we are going to talk a little bit about the transcritical heat pumps, which is basically, let's say, the evaporation happens still in the two-phase zone, but their condensation can happen above the critical point of each working fluid. And this part, I'm going to hand it to Fred to present.
Thanks. Like Mustafa explained really well. I really love his tool, having like a range of possibility, not having the best optimal solution. I think it's really important for people working with company. Like he pointed out, his solution are for subcritical, which is really relevant in many industry. But sometimes industry, like for in this case, like that's just an example for propane heat pumps, you can see the heat source is quite flat. There will be the heat source and the heat sink. So the heat provided for the industry is quite flat as well, which is relevant in many industry. But in some cases, sometimes for heating air or heating some water, the heat in the industry will have a temperature slide. And for this case, we can use transcritical, and there's a nice graph being done recently from a student, exchange student in our lab. So you can see the difference if the cycle, that's for propane, is transcritical, the heat deliver has a much higher slide. Temperature glide, sorry. So as you can see here, that's for subcritical and for transcritical. And you can observe that the heat source didn't change anything. It's really just the heat sink. So that's, I think it's really relevant. I want to show you other example. Just to come back for what, let me show you my face as well, if it's working. So that's what Mustafa was saying. In some industry, you have ground composite curve, and with that, oh, sorry, yeah, oh, my, back to that. Perfect. So in case you have one heat pump, subcritical heat pumps, you can see you can have a typical efficiency, but if you know a bit of the pinch analysis, you can see all this area between the heat desire at different temperature from the industry and the heat delivered by the heat pump. There is actually a mismatch. So what we would like is to have less mismatch. One solution, like really well presented by Mostafa, is to have different heat pumps. So each heat pump will deliver the heat at certain part of the industrial processes. And the other solution, what I want to present, is the transcritical solution. So using a transcritical cycle, you can deliver heat which will match more the application. That's already, there is already some example. I show quickly just one, the Transpac, which is from the Dalkia, so it's a EDF group. It was made, I think it's running since 1 year in France. And they're heating air from 95 degrees to 140 degrees. So you can see the demand is really like a deep temperature slide, and the source is around 70 degrees, and they achieve a COP of 3.5. And that's the graph they are presenting, they are showing. So like I say, we can clearly see it's a transcritical. The refrigerant they're using, HFO, it's a R1234ZE, and the outside of the compressor, it's 165, and the gas is being cooled until 100 degrees, so it can heat the air from around 95 degrees to 140 degrees. So that's an example of a transcritical heat pump being already implemented in an industry. What we would like as well to see, you can see on the bottom, on the heat source, it would be nice as well if we can fit and match the heat source to the industrial demand. So for that, there's two solutions. One is the reverse Brayton heat pump, which is a heat pump which the refrigerant stay in the gas and the gas phase, and the other is using a refrigerant mixture. Reverse Brayton heat pumps, there is only one example that I know of. It's from the company ECOP, Austrian company. They already installed a heat pump in a few district heating in sorry, I will move myself in Vienna, and they can achieve a certain COP, and they have limitation. I don't go into much detail, but just to know that this kind of heat pump exists. Mostly there's only the ECOP solution, but it's something which is already being installed right now. The other is about heat pump with refrigerant mixture, and it's something we are really working on in my lab, especially due to a bridge project we had received from the government, working with the ETH together, and having a mixture of refrigerant which is not which is customized, allow to have this kind of temperature glide for in the two heat exchanger. So you can see if it's all blue, the lines are flat, so that means it will give and use no temperature glide, so fixed temperature. But when you are starting mixing two different refrigerant, you have different glide, and it allows to having, with using the same heat pump, depending of the mixture, you can really fit the application of the industry. And there's another effect as well. For the same compressor, same size of heat pumps, depending of the mixture, you can increase the heat capacity of the heat pump. And that's not only fiction, it will be made at the end of this year by Sheco, and it will be installed by the Lind and Sprungli. It will increase the COP. They will start actually with a pure fluid, I think isobutane, and after they will add another refrigerant to have a special mixture to increase the COP and to increase the heat capacity of the heat pump. So yeah, that's the two solutions to try to match the heat pump delivering heat to the application of the industry with using, so it's two non-subcritical industrial heat pumps, the transcritical and the refrigerant mixture, and they are becoming a reality. That's why we want to work with Mostafa, so he could try to implement this solution to have a really the optimized solution. I think that's all for my part. Thank you very much, and I give the floor to Mostafa back.
Thank you, Fred, for presenting this nice work. And you talked about the transcritical and the mixtures. So I believe that what you're talking about, it can be implemented in the logic that we have in ASTRA, and it will make it a relatively complete work by considering all the opportunities from subcritical heat pumps to supercritical, and it would be very interesting. So far, we talked about the logic of ASTRA and what is able to do, and the project that we are thinking about to collaborate with OST. But from now on, I'm going to talk about some ideas that we have for this model. And this is exactly where your inputs are quite valuable for us in order to shape the future of our platform. So I will start with this slide, which says the real question is not only which heat pump, because so far the idea behind ASTRA was to make it a generalizable model that no matter what is the input from which industry it is, the system can automatically detect and find the solutions, the viable solutions. But that's not the only thing that we should get from the industry, because everything is not just process stream data. There are so many constraints that each site might have and makes the analysis very site specific. But in order to still keep it generalizable, industries, they want to know how the solution that we are providing can fit into their existing facilities, or which waste heats they can really recover, and how the load between the boiler that they apparently might have with the heat pump, how much this load can be exchanged between the two, and other constraints that each site might have. For example, one of the options is the retrofit option, because most sites don't start from zero, and we don't always start from the scratch to design. It's not a grassroots design. There's always already the equipments and the facilities that the site has. And what we should be able to do is to identify the best upgrade path, how to integrate the heat pump in the existing facilities in order to reduce the emissions, lower the operating costs, and to be basically greener. Also, in terms of working fluids, technically speaking, we always say that if you want to cover a certain temperature for each site, if they have, let's say, a steam demand at 180, there are certain working fluids can thermophysically are able to prepare this, to provide this demand for the industry. But this is the technical part. The other part is that different industries, they have different regulations, and because of their products, they are not always allowed to use, let's say, certain working fluids within their site. For example, in food, in paper industry, they might be hesitant to use certain working fluids because of flammability, toxicity, and other things that can risk their whole process. So we have to consider all these limitations for each industrial case, and then let's say we don't have much of an option to do the optimization for that, and we should satisfy the demand of the user. The other option that can be integrated in this is that the user be able to define the reality of the site. For example, a site might say, I have a space limitation for having a heat pump unit, and these are my limitations. So the size of the solution that you're proposing shouldn't exceed this. So we should be able to kind of integrate this into our model, that be able to filter the whole solutions that we have by this to come up with the practical solutions that in the end can be useful for industries. The other thing is that how much of their waste heat is available or is accessible easily, or even how much is their budget, the maximum budget that they can spend, or what is the payback that they are it's preferable for them. About the temperature and pressures, their piping system or the connectors might not be able to be able to handle these pressures or temperatures. They might have a limitation there. And also about the working fluids we talked in the previous slide. So all these solutions should go through these filters. And then finally, we will come up with the only solutions that are able to satisfy the demand of the industry and pass their, let's say, limitations. So here, as an example, we see that this already exists in the model, that the user can easily define their delta T mean. And with this, they can say how much heat recovery they might have. So as we see, when the delta T mean decreases, the heat recovery increases, and vice versa. So this is one of the possibilities in ASTRA, that we try to make it flexible enough that the user can change a variable and quickly see how the configuration is changing due to that change, which won't be the case in, let's say, similar applications, which, as I said, they might take hours to do that. So if we can really have a short runtime, these are all the advantages we might have in our model. And on the right side, we see that how this change of delta T or heat recovery would affect the GCC, and consequently the decisions, the let's say optimal solutions that we will provide for the site. The other interesting option that I really like, and I think it should be added to the model, is the sensitivity analysis. Because imagine we come up with some solutions, option A, B, C, and the user, the industry, wants to know if this solution, okay, this solution currently is good, perfect, satisfy everything, but if this solution is resilient enough against the economy variations, the change of energy price, the CO2 tax, and so on. So the user can be able to define ranges for the energy price and so on, and see if this solution is still viable or is changing a lot. And then this will really change their decision in choosing one of the options. Here is a simple example of that. For example, in case of A, we have an electricity price and we increased it to case B. And as we can see, the algorithm goes toward more segmentation, choosing more levels of evaporator and condenser. And with this is basically the temperature lifts are becoming smaller, and that's why the COP also goes higher. But why it behaves like this? The reason is simple, because when we increase the electricity price, the algorithm goes to our more efficient systems to compensate the cost of electricity. And last but not least, this option can also be useful and interesting for non-expert users, which I think we are all living in the era of AI. So we can power such models with large language models, and then the non-expert user will be able to just talk to the model, and based on the agents, the works can be done for the user. Yeah, for example, translation is a, I think, easy, low-hanging fruit for large language models. So there is no language barrier in that case. Also, in terms of outputs, you will not only get numerical outputs, you can ask for different formats of outputs, tables, graphs, and so on. And with this slide, I wanted to end my presentation by saying that we talked about these ideas. There are very raw ideas, but we're really looking forward to your feedback, because it really helps us to shape this platform and strengthen it to be really useful for you, not just a research tool, but an industrial decision support platform. Because with your feedback, we can really prioritize which additions are critical, are useful to have. Also, yeah, we can define all those constraints that I talked about, very case specific, but it makes the model generalizable to be able to handle different sites and so on. And for this part, we also prepared a very short questionnaire. I'm sure it won't take your time much, but it will mean a lot for us. And I will hand it to Fred again to go through this questionnaire for us.
Perfect. Thank you very much. Yeah, indeed. I think I totally agree. Actually, I even push a bit Mustafa to do this webinar to get some interesting feedback from you, because making a really brilliant tool, if it doesn't fit the need, I think it's a bit waste. And I really like the tool Mustafa is building, so I would really like that is useful for everyone. So the QR code is there. We can go quickly together. So there is a couple of questions. First of all, how relevant is this tool for your work? If it's not relevant at all, just leave it. Or if you click, I think you can always remove it. So in my case, I do some case studies, so it's quite relevant. And then there will be which ASTRA capability will be most useful for you. You can drag and drop. And if there is something we missed, you can put other, and you can add some of what you would like to see here. So that's for the second question. The main barrier to implement high temperature heat pump and even normal temperature heat pumps in industry in your project. The one I saw mostly during my few case study was really the high capex. It stopped a couple of company. Some other, there was a lack of process data, or it was hard to know exactly what was the best. So please, if it's all of them, just back to all of them. If we miss something, sorry, just add it yourself. Maximum process temperature level, in case you're an end user, you can feel that, or even if you're like you implement some heat pumps, you can see, oh, most of the time they are below 100 degrees. Could you imagine using ASTRA for this? Like we're speaking, it's really for early stage, for pre-study or beginning of a study. Yes, maybe it will be interesting, because it may show us that you're interested, but maybe the tool doesn't fulfill everything. So please, if you click maybe, we will love that you give us an email so we can try to have a meeting with you and try to change or improve a bit this tool. Which access model will be most useful to us? As a researcher, for me, that's open access or academic version. Some people would like to have a really professional version that could be discussed. Will you be interested in receiving update, just in case you want to know about the development of this tool and which category of your organization? And if you would like that we contact you and keep in touch, you can give us your email and we will do it. And of course, give us any feedback. So I can see there was already five answer. You can do that in the future. We will leave it open. I'm already really happy to see already 2/3 of the people can imagine using ASTRA, so it's really good news. So thanks a lot for participating to this webinar. Thanks a lot for replying to the survey, and we'll be really happy to have a chat with you if you are interested more. I leave the last word to Mustafa because that's mostly his baby. Thank you very much from my side.
Yeah, thank you so much, Fred. Actually, there is nothing to add. You mentioned everything. I just wanted to say that, yeah, if you have any comments, if you're interested, or if you feel like something is missing, you can always write to us, me or Fred, and we would also like, if you're interested, we go to one-on-one meetings and so on to know about your problems at your site or your limitations. And yeah, I mean, the goal is that if you're able to push the model as further as possible, considering all the technical aspects, the ideal thing doesn't exist, but the sky is the limit. We always like to push the limits and go further and improve it as much as possible. Thank you very much.
Thank you very much, everyone. And yeah, have a nice day, everyone. Thank you, Mustafa. And
Thank you.
I hope to hear from you really soon.
Thank you very much.
Have a
Bye
nice
bye.
day. Bye-bye.